All right, I'm going to carry on with the math, the sort of talking about the math, but I'm going to assume that you already watched this derivation. So if you didn't watch the derivation, um, it's on you to, well, go back and watch the derivation. What I like about it, and it's probably mentioned in the other video, is it's a nice throwback to when we learned about energy and momentum. Just a neat little application of that. Um, that derivation, I think originally was credited to a guy named Compton. Later in the development of quantum, this guy's kind of famous, a French guy. I've heard his name pronounced de Broglie. I've heard his name pronounced de Broglie. I'm not very good at French pronunciation, so I'll kind of back and forth. We use different versions of it. But this de Broglie guy, he was doing math a completely different way, but still looking at this wave nature of electrons. And from a completely different, much more complicated math background, he got lambda of the electron equals Planck's constant divided by momentum, which is kind of cool because it's the exact same equation that we got in our derivation. It's just algebraically flipped around. But what's deeper coolness about it is this de Broglie guy got it a completely different way. So it's neat that we have two completely different methods leading to the same basic equation. Basically what de Broglie said is quantum particles have a wavelength, and that wavelength is related to their momentum. Electron microscopes. Sometimes I ask people to find an electron microscope diagram and do a little bit of research why electron microscopes are better. Electron microscopes are based on this quantum idea here, that particles with momentum have a wavelength. So they use a parallel plate, they shoot electrons, they use cool ways to focus them like a lens for light, but more complicated. But when they shoot these electrons, we could figure out the momentum of a flying electron. We could have done that back when we learned about parallel plates. We could have figured out how fast they're going from the voltage, and from how fast they're going, use our momentum equation and figure out their momentum. Once we know their momentum, we can figure out their wavelength. And it turns out, figure out the wavelength using this new de Broglie equation. It turns out that their wavelength is way, way, way shorter than the wavelength of light. From unit 4, we know light is in the hundreds of nanometers. These are in like a fraction of a micrometer down into the nanometers and shorter. So shorter than nanometers. Since electrons have a shorter wavelength in their quantum nature, they actually do a better job of seeing tiny things. So electron microscopes do a better job than light microscopes because electron microscopes have a shorter wavelength. These cool electron microscopes that we've all heard about, they only make sense if we can engineer and take advantage of the quantum nature of the electron. So it may sound crazy and science fiction-y to imagine an electron as this particle that's flying with a wavelength property, but it works, it's real. I got a couple examples for you to work through here, 3 examples. Work through them, check the solutions, make sure they make sense. This last one is probably the most important one. Hint, hint, physics teachers, we love this kind of question because it brings in lots of stuff. If we just tell you that the electron's accelerated by 2000 volts, you need to use the voltage to figure out the speed. That's like unit 3 energy and momentum kind of stuff, parallel plate stuff. Use the voltage to figure out the speed, and then from the speed, you can use that de Broglie equation to figure out its wavelength. So try those. The check-in is related to this stuff. There's a worksheet there for you to look at. Oops, a couple worksheets for you there to look at. I'm going to pause this video, but we're not quite done. I want you to learn a little bit more. We got to backtrack, and earlier on, when we started quantum, I said one of the instances was Bohr-Rutherford model can't be right. I don't want to leave you hanging. We got to come back and fix the Bohr-Rutherford model.